summary of, oh, come on. Like taking a general summary of the liver function, what the liver does. Where's the pen? So it performs several important, really important metabolic functions. First, okay, it metabolizes glucose and fat. That's really so. Glucose that is absorbed in the intestine goes into the broad biportal circulation into the liver. Liver converts it into the glycogen. Liver converts it to fat if there is too much glycogen. Lipids also being stored as the fat or used as the energy source. So liver is one of the major metabolic intermediaries. Okay, so here and here. It makes proteins, blood proteins, okay? Albumin, which is the major component of the plasma, okay? Liver produces a bunch of the proteins that transport things in the plasma. Remember we were talking about the thyroid hormone and how thyroid hormone, when it is released into the blood, has to be transported because it's fat soluble. So those transport proteins, so-called beta globins, are synthesized by liver. Clotting factors, proteins that are responsible for plugging the hole in the wall of the blood vessel. Okay, also liver. Does that make sense? Well, it does produce bile. We talked about it, and it as a component of the bile, it releases bilirubin. Does anyone remember? Bilirubin is the product of degradation of what? Well, red blood heme, yes. So heme that is usually normally toxic is metabolized into the bilirubin, and bilirubin is released, excreted by the liver, and that what gives fecal matter the brown color. Okay. What else? Detoxification. Well, when we say detoxification, we mean a lot of things. First of all, penicillin, I don't know, any antibiotic, pretty much all the drugs, are they toxic? The dose makes the poison, okay? But they're all toxic. So liver gets rid of them. You know, successfully or not so successfully, but it does. So that's a very important thing. For instance, ethanol is the drug, and it is a drug in terms of, you know, people can get drugged by ethanol. It's a toxin, and liver gets rid of it. Okay. It produces urine, uric acid from the products of, for example, protein metabolism. Okay, from the products of ethanol metabolism. And finally, those molecules, those drugs, those toxins are excreted in the bile. And many microbes that enter the bloodstream will be caught and destroyed by the Kupffer cells in the liver, the macrophages. Now, taken all together, you see, that's kind of an incredible list of features. Yes? Penicillin is toxic. Same goes for Tylenol. Well, when they say Tylenol is hepatotoxic, that is true. It is. And a colleague of mine, when he was doing PhD thesis, he studied something like a role of immune system and the toxic liver damage caused by Tylenol. And he gave, I think he gave rats, I think those were rats, certain dose of Tylenol. Well, out of curiosity, we recalculated it to the amount of Tylenol that people should have drunk to get the same exposure. It's like 3 pints or something. So I mean, if you're really determined, you can do that, and you can ruin your liver forever, but it's like really hard. Okay, so it does liver damage, but not to the extent that is often propagated. Yes.
So the high enough amount would cause liver damage for certain, but if you take a low enough amount, say every day for your life, will you have?
For Tylenol, I don't really know. I don't really know when there's a if there is a boundary for the chronic exposure that will affect the liver function. If there is such a boundary.
Like alcohol, you have damage your liver.
Yes, absolutely.
Over a lifetime of drinking.
Correct. Correct. But here's the thing. Again, the dose. And I will kind of brighten up the otherwise. Sometimes I understand. Sometimes it's a dull subject, but I want to discuss something with you. Well, first of all, since Hunter brought it up, the alcoholics, okay, so liver cirrhosis. So what happens is constant exposure to elevated doses of toxin, so pretty much drinking too much, causes inflammation, damage to the liver, okay? How our body deals with the damage? What do you do when something is broken in your house? You fix it. Well, throw away would be nice. Well, it depends on what, you know? If that's like a chimney, you can't really throw it away. You have to repair it. So body repairs the damaged tissue, the injury. Okay, it gets repaired. Repair is accompanied by inflammation. And the result of repair, as we discussed when we talked about skin repair, for example, is connective tissue. Think about this. Skin gets broken, connective tissue will regrow, epithelial tissue will regrow. Bone gets broken. Bone is connective tissue, it will regrow. Ligaments will get broken. They will very, very slowly and painfully regrow. Skeletal muscle gets broken, well, gets kind of torn out. Nothing will regrow. It's a muscle, it's not connective tissue. I mean, connective tissue will substitute for the lost muscle. Functionally, it's not the same. Same happens in the liver. Connective tissue substitutes hepatocytes. Can it produce bile? Nope. Can it detoxify? Nope. So liver function declines. And it declines with age. Now, what can cause liver inflammation? Exposure to toxins, like alcohol. What else? What can cause inflammation? Hepatitis. We generally refer to hepatitis as inflammation of the liver, but I know what you're referring to. Infection, right? A, B, C, D, E. There are 5 hepatitis viruses. They can be other causes, yeah, not necessarily viral. Some of them are acute, like Hep A. Some of them are chronic, like Hep B or Hep C. Okay, acute is fine. Liver gets inflamed, you get jaundiced, virus is gone, you're normal again. Nothing really bad. Okay, what else? What else can cause inflammation? The disease that affects 33% of the US population. Not diabetes. It would be awful if 33%. Imagine that third of this class is diabetes. No, not diabetes is about 10%. But you're close. Obesity. Specifically obesity. So-called non-alcoholic. You can find this acronym sometimes. Non-alcoholic fatty liver disease. Accumulation of fat in the liver causes inflammation. It's fascinating, actually. Fat contains a lot of inflammatory cells. Not every fat. For instance, if you would look at some, mostly men, I think we talked about it, but mostly men are prone to accumulation of so-called visceral fat. When we say visceral, what do we refer to? Organs, yes. Fat that is accumulating around organs, mostly in abdominal cavity. So you can see men that otherwise look fairly healthy with the gigantic bellies. That's visceral, so-called visceral adiposity. If you're curious, it's kind of lovely chart. Visceral adiposity. Okay. Now, interesting. Yes. Yes. Chew your mouth. Stop eating. I always say that I can treat obesity. Like, if you want to pay $400 for some shrink, give me half of that. I will chain you to the pole in my basement, and in 2 weeks you will be cured. So, David, you mean drugs or something else? Only diet or exercise. That's the only. Okay, since it came up, treatment for obesity, diet and exercise. You can cut it out. Yes, trust me, you're not the only one. I remember myself after Christmas, 20 pounds like this, and they're all here. Okay, so the only thing you can do about it is diet and exercise, and there are multiple studies that show that, first of all, if you diet, it's not sustainable. We all know, from the January 1st, the New Year resolution is to eat healthy. Screw that in a week of something when you go to the restaurant, okay, or you find in some hidden place you find a bar of chocolate. Okay, so it shouldn't be a diet; it should be a lifestyle. Exercise is more interesting. There were multiple studies that demonstrated that in people who only exercised and didn't look after they diet, actually gained weight, because the hunger that they experience after they exercise, they consume more calories than they spend. It's amazing how many calories we eat and how little we spend. Okay. The bariatric surgery, trim the stomach, very effective, not sustainable, because if person does not change the dietary habits, stomach can stretch. Drugs only if it's like a leptin deficiency, then drugs will help. But other than that, no. Now, going back to visceral adiposity, there's another type of adiposity, subcutaneous. Do you know who is more prone to subcutaneous rather than visceral? Women, yes. Women develop adipose tissue more under the skin. Turns out that subcutaneous adiposity is healthier. It's pretty much healthy. Fat that accumulates under the skin is not inflammatory. And there is a hypothesis that probably this fat evolutionary helps women to survive in case there's a shortage of food, while men are obviously dispensable material. They aren't needed to for reproduction in a long-term perspective. Okay. And fat is inflammatory. Fat in the liver is inflammatory, and I had a chance to look at the normal mouse liver and fatty mouse liver, and that's awful. There's more fat than liver tissue. Now, going back to cirrhosis. So in cirrhosis, constant inflammation of the liver causes the hepatocytes to be substituted by the connective tissue. For instance, in non-alcoholic fatty liver disease, fat is the connective tissue. Does that make sense? So when you get less and less hepatocytes, obviously, I'm going to trip over that wire eventually. Obviously, what's going to happen is your liver will stop working. Your liver will stop performing its function. Now let's take again a look at the function. Metabolism, well, okay, sad, but we probably can just feed ourselves glucose. But look at something here. Protein synthesis. So immediately the blood problems start. No normal clotting, albumin levels change. It causes edema because of the altered fluid balance between the blood and the tissue. Secretory functions get completely screwed up. So bilirubin is not properly excreted, which means accumulation of bilirubin in the blood and potential kidney toxicity. Hormones are not properly excreted. And I mostly refer to fat-soluble hormones that are based on the sterols. Can you name fat-soluble hormones that we produce on a regular basis made out of sterols? Cholesterol is not a hormone, it's a precursor. But yeah, cholesterol levels rise. Huh? No, it's not sterol, it's thyroid hormone. Corticosteroids, we produce them in response usually, they're low levels. It's corticosteroids. Look lower. Testosterone and estrogen. And what happens in people with advanced stages of cirrhosis? Their liver do not excrete estrogen properly. And they develop a condition that is known as gynecomastia. When they start to grow breasts. That is because estrogen that men normally produce, but it's not, doesn't regulate the function, it's excreted by the liver. It stops being excreted and there you go. Okay? So these are the causes of cirrhosis. Cirrhosis, moreover, can lead to the development of the liver cancer, okay, which is not extremely frequent, probably because people with cirrhosis may not just live till they develop liver cancer, they die earlier. I wanted to say something about this thing. Oh, to highlight how important liver is. What is the average time a person can survive without liver? Like, you open somebody up, cut the liver out, and throw it away, stitch the blood vessels. Say again? Hours. No. Minutes? No, it's too little. 18. About, 12 to 24 hours without the liver. Okay, and then person's dead. Just for comparison, without functional kidneys, both kidneys, person can live up to 10 days. I'm not saying that kidneys are dispensable, but the good thing about liver is that it can regrow, it can regenerate. So in some cases, removal of one of the lobes is sufficient, especially if it's a cancer. You can remove a lobe of the liver. That makes sense? And it will grow back. It will increase in size. It will regenerate. It's kind of an interesting thing. Yes?
How much damage needs to be done for it to be considered then liver failure and stuff like that? Or
I don't know the clinical...
I didn't know if it was like a certain percentage of the liver.
It probably is, but I think liver failure would be judged based on the blood clotting properties, for example, and levels of certain toxic markers, like maybe levels of urea, levels of estrogen in men, levels of testosterone in women, levels of cholesterol in the blood. Okay, and that should point that this person doesn't eat like 2 pigs a day. That's why his cholesterol is skyrocketing. But because cholesterol is high because of the liver failure. Now, alcohol, the favorite topic, right? Little disclaimer, I'm not encouraging drinking here. But is there a safe amount of alcohol consumed every day? Exactly. Well, again, so science doesn't operate with anecdotes. I always give example of my favorite anecdote. It's an actual story, a true story. One of the oldest, from time to time, the oldest person on earth changes. When the previous one dies, we have a new oldest person. So one year, it was something like 15 years ago something, the oldest person in the entire world was some French woman, who was 118, pretty old. And she looked not senile, she was sane and bright and everything was good. And she quit smoking at the age of 116. She started when she was 16, smoked for 100 years, and then quit. Does that mean that if you smoke for 100 years, you're going to live 100 years? Probably not. Okay? So that's an anecdote, which is no doubt interesting. Like, look at Ozzy Osbourne. This dude should have been dead in 1980. He's still around. And he's going to dance at my funeral, I think. Now, that's an anecdote too. It doesn't mean that you have to drink 4 bottles of cognac every day for 2 years. So when we talk about science, we talk about statistics, big numbers. So there was a study, and I think I may have the actual paper in the computer. So what they've studied, they asked the question, is there an optimal amount of alcohol? Okay? Or if you increase consumption, so they pretty much asked the damage, D, and the volume of alcohol consumed daily, do they follow this dependence on average? This or anything like that? So, you increase the damage. That makes sense? It turns out, the answer is no. Because if you look not at specific organs, but at the outcome as longevity, okay, the time of survival, risk of dying, turns out that the curve looks like this. So this is the amount of alcohol. If you consume that much alcohol every day, you have the lowest risk of dying. So there's some benefit in it. They didn't study what type of benefit it is, but I saw this graph with my own eyes. So implications are, that's kind of provocative thought. First of all, if you drink, and I think it was something like 2 to 3 drinks a day, something like 40 to 50 30 milliliters of pure ethanol a day, which is a lot, and it amounts to maybe 2-3 bottles of beer, something like that. Anyway, it means that if you consume that much alcohol, you have lower risks of dying than people who totally abstain of it. And it kind of makes life better, doesn't it? I like this idea. But what's even more provocative is that if you drink twice as much, you have the same chances of dying as the person who doesn't drink at all. Okay? That makes me feel even better. Now you have to appreciate that we don't talk about situation when you abstain from drinking for 2 weeks and then binge in just 3 bottles of whiskey in one day. No. That's chronic in a good way, chronic permanent exposure, regular consumption of certain amounts. And it turns out that for a lot of things that we deem dangerous, meat, pork, butter, saturated fats, the curve looks pretty much like this. So there's some optimal amount of stuff that you eat, drink, that will give you some benefit. Okay?
You said they don't know what the benefit is. Like,
They didn't
what it is.
They didn't look. They didn't look. And benefits can be huge. I'm too lazy to try and find this article in Onion. Do you know Onion? Onion, the most trustworthy news outlet in the United States. They published an article which says, if you've never read Onion, go there, theonion.com. They published an article in which they suggest that people who drink, smoke, and eat meat live shorter but much happier lives than those who don't. Which kind of makes sense, okay? I don't know about shorter, because think about this. Let's admit alcohol is the drug, it is a toxin, and it relieves stress. Maybe that's the positive effect. It reduces the cortisol level, it reduces the level of stress. It was shown that people who socialize generally have higher longevity. Come on, alcohol helps us to socialize. That may contribute as well. There probably are some physiological effects of alcohol. So I think it's multi-dimensional. Gallbladder, the boring organ. Okay? It's located underneath the liver. Okay? So if you think about the whole bile thing, when bile salts are released in the duodenum, they are taken back through the hepatic circulation back into the liver. So that circulation of the bile salts additionally stimulate the liver production. The bile production. It actually establishes a positive feedback. And bile continues to accumulate, and eventually the amount of bile produced exceeds the needs of the duodenum in terms of the digestion. So you have to store it. And gallbladder does exactly this. Okay? Gallbladder stores the bile, and not only this, it concentrates it. Okay? Makes kind of sucks out of water. Does that make sense? Now, when food, well, it's not food anymore, it's chyme, enters the duodenum, gallbladder contracts and releases the bile. Remember, CCK stimulates the contractions of the gallbladder, and gallbladder releases that concentrated bile into the duodenum. So when chyme is fatty, bile starts to break down the fat droplets right away. Right? No, I don't want to do anything with that. Thank you very much. Thank you very much. Thank you very much. So it has 3 layers: mucosal layer, muscularis, and cirrhosis. There's no submucosa. It's fairly thin-walled. Okay, and it's connected to the duodenum via the sort of succession of ducts. So here's how bile travels from liver and from the gallbladder. The right lobe of the liver empties its bile into the right hepatic duct. Left lobe into the left hepatic duct. They merge and form common hepatic duct. You can see common hepatic duct right here in this picture on the right. Okay, so that's the common hepatic duct. Common hepatic duct merges with the cystic duct, and together they form the common bile duct over here. And then finally, common bile duct releases the bile into the duodenum. At the hepatopancreatic ampulla, though, common bile duct, as you may remember, right here, you can see that image. Common bile duct merges with the pancreatic duct that carries pancreatic juice containing bicarbonate and digestive enzymes towards the duodenum too. So hepatopancreatic ampulla here releases the mixture of bile and pancreatic juice into the duodenum. And that release is regulated by the hepatopancreatic sphincter. Right? It makes a lot of sense if you think about the function of those secretions. What is their function, main function? The bile and, digestion. Well, you got to digest when what is in the duodenum? Chyme, yes, the partially digested food materials, right? When there's no chyme, you don't have to release that, so that sphincter regulates whether it releases it or not, right? Now, bile can get concentrated in a gallbladder, and if it is concentrated too much, like if you put solution of salt on the stove and start to boil it, water will evaporate, salt will be more and more concentrated, and eventually it will start to fall as crystals, right? Same happens in the gallbladder. When bile becomes too concentrated, it forms gallstones that consist of cholesterol, calcium carbonate, bile salts. So being white, obese female is what plays as the risk factor towards gallstone formation. Sedentary lifestyle and age. They vary in size. So this is the gallbladder, and you can see that it's it's pretty large, distended. Okay, now think about this: when such a gallstone blocks the cystic duct right here, okay, it causes the distension, the inflammation, and pain, right? And then the pain is right hypochondriac region. It's very focused, pretty much right here, and you get admitted into the hospital, they cut it out, and you're out pretty much next day. Okay, so yes.
Do you have to be like a white obese female? Because a friend of mine, this happened to him a few years ago, and he was extremely active and wasn't obese at all, and he passed with 3 gallstones. He was admitted to the hospital. Like, so does it just like kind of vary, but like it's more common?
You kind of answered your own question. No, you don't have to. It's a risk factor. Does that make sense? Like that woman that smoked for 100 years. She didn't catch the lung cancer. Does it mean that nobody will? No, she was lucky. Okay, so your friend was unlucky. He was active, sporty, and whatnot, but still formed the gallstones. It can happen. Okay? Now, bile will still be produced, because what produces bile? Which organ produces bile? Liver. Gallbladder doesn't make it, it just stores it. So you get rid of the storage. The only problem is, since the bile is not concentrated anymore, if you eat something really, really fatty, you're going to feel indigestion, because the time that it takes liver to start to produce enough bile to digest that fat, it's kind of extended now. If you would have a gallbladder, you eat something fatty, gallbladder releases the bile and fat starts to get broken down almost right away. Now, here's the little statement here. I love it. Very incisive. I always give this number. Wild guesses. The size of the largest gallstone that was ever extracted from a person. The largest. And person survived. That's important. I don't know about people that didn't survive, but it was a woman, like 60 something, and gallstone was taken together with a gallbladder, of course. She survived. Weight. Yes. Come on. Okay, a pound there. Any other guesses? You can go up, you can go down. I will tell you the right answer. Let's do 3 tries. A pound. Half pound. 2 pounds. 14 pounds. 6.29 kilograms. The largest gallstone that was ever taken out of the person. Yeah, it was like this big. Huh? Yeah, 2 or 4 pounds.
If it's seriously that big, if your liver is what, like?
It's not in the liver, it's in the gallbladder.
I'm just trying to think, like, wouldn't it like push on your other organs? Like, how does it like bigger than baby?
Yeah. So you would be surprised.
Cause liver damage because it is basically there.
Well, perhaps it didn't cause the damage per se. It was probably pushing on the liver a little bit. But it blocked only the bile release from the gallbladder. And if you are amazed about the fact that she was admitted to the hospital with a gallstone that big, I suggest you look at the pictures of symptoms of secondary syphilis and head and neck cancer. The only question that I always had, how can you not go to doctor before you have this? Because especially in a head and neck cancer, people develop lesions that are disfiguring, horribly disfiguring, and they do not develop them overnight, but they still, I don't know, it's going to get better. No, it won't. Okay? There are multiple cases of people who didn't know, well, women that didn't realize that they were pregnant until they went into labor. There was a case of morbidly obese woman. When she was admitted to the hospital, they managed to find several like pens and pencils in the folds. Yeah. So, you know, things happen with people. Huh? Yeah, so it is interesting, surprising, but not that surprising. Okay. Pancreas. So that's the lovely organ. Pinkish, you see that pink stuff here? That's the pink organ. Shapes somewhat, as one student told me, shaped like a fish. Which with some fantasy you can appreciate. So it's retroperitoneal, it's not surrounded by the peritoneal membrane. And it can be loosely divided in 3 parts. The head, which is closest to the duodenum, the tail, which is closest to the spleen, and the body, which is in between. Right? Anatomically, does that make sense? Head, body, tail. This organ has both endocrine and exocrine functions. Remind me, what are the endocrine functions? What? Yes, insulin glucagon, regulating blood glucose. Okay, the Langerhans islets responsible for that. Now, the acinar cells, located in so-called acini, acinus is the singular, acini is plural. Acinar cells produce pancreatic juice. Okay, they release a number of enzymes containing in the zymogen granules. Okay, and they also produce bicarbonate ion. Does that make sense? Now, zymo means enzyme. Just Greek word. So zyme. Actually, in Greek, zyme means yeast. That's why enzymes are called enzymes. So enzymes, digestive enzymes, and bicarbonate ion, right? Remember we talked about two hormones that are produced by duodenum when Kim enters into the duodenum. What are they? CCK and secretin. Yes, secretin and CCK. Now, these hormones, their production, it's in response to which two chemical stimuli? Acid, obviously. Kim comes from the stomach, and fat. Remember, CCK pretty much stimulates, well, they both stimulate the release of bile from the gallbladder and production of bile by the liver. Okay, but CCK specifically, cholecystokinin, specifically is responsible for stimulation of digestive enzymes, while secretin stimulates production of the bicarbonate. So you got to have both to stimulate right pancreatic juice. Does that make sense? Does it? And let me show. Okay, and fat stimulates CCK production, and acid stimulates secretin production. That makes sense? No? Courtney, no. Really, if it doesn't, just, I really like to hear the phrase, no, it does not make any sense. Can you say it again? Because I don't want to listen it right after the exam. It did not make any sense. Okay? That makes sense? That's kind of a quick, dirty flowchart. We're going to go to our favorite subject, chemistry. I know you all love chemistry. We talked about that already. When we discussed the parietal cells in the stomach, what do parietal cells produce? Hydrochloric acid, right? So we discussed how they make acid. Can anyone remind me what we need to make acid? Water and carbon dioxide. And when they are mixed together, what happens? What do they produce first? Yes, the carbonic acid. And carbonic acid dissociates into what? Hydrogen ion and bingo, bicarbonate ion. Okay, now this, is that acid or base? Acid. Well, if this is acid, that is supposed to be base. Now, we needed acid in the stomach, but we don't need the acid anymore. Does that make sense? We don't need. Now we need base produced by the pancreas to neutralize acid that just entered duodenum from the stomach. Does that make sense? So that exact reaction, you see, that exact reaction produces base and the acid. But in this case, we transport bicarbonate ion into the lumen of the pancreatic duct, and we get rid of the proton. We dump it into the blood. Does that make sense? So you see, again, the same exact reaction. I can go back and show it to you. I can go back to the parietal cells and show you that it's exactly the same reaction. We produce carbonic acid splits into the hydrogen ion and bicarbonate. And in the stomach, we need hydrogen ion, we pump it in the lumen, we get rid of the bicarbonate. In the pancreas, it's all the opposite, we need bicarbonate. It goes into the duct, ends up in the duodenum. Acid, hydrogen ion, we dump it into the blood. Does that make sense? Okay? We good? Right? Okay, so that's pretty much the brief summary here. You can refer to this textual explanation. In that statement, pancreatic juice also contains a number of digestive enzymes. Yeah, it's true. It kind of same statement as to say that the Beatles was the popular band. Kind of underestimation. Okay. So let's take a look at those enzymes. Here's how we're going to chat about them. We're going to talk about first the name of the enzyme, and we're going to discuss what it does. So first is going to be trypsin. Okay? We'll get to where it comes from, what activates it, and blah, blah, blah. Trypsin. It cleaves internal peptide bonds. That sophisticated statement means what is the substrate for trypsin? What it breaks down? Proteins. Does that make sense? Because peptide bonds. So substrate. I'm going to do another column here. Substrate. Protein. Now, how does it break down protein? Does it eat the amino acids one by one from the end, or just slashes it in two halves? Look at this word, internal. So, trypsin, what it does, I'm going to make a mess. So if this is protein, that's what trypsin does. Okay? It not necessarily will be in the middle. Okay? It can be like 1/3 of it. Does that make sense? Like this. But it's going to be big chunks. Does that make sense? So it breaks large proteins into smaller chunks by cutting them in the center. Like you take a loaf of bread and you want to freeze half of it. And you cut it in the middle, you freeze one half, and you eat another one. Does that make sense? Chymotrypsin, same. Elastase, same. They work even the same way. They also break down the peptide bonds inside the protein. Does that make sense? So that's going to be elastase. That's going to be chymotrypsin. Okay? Now, carboxypeptidase. We've already encountered a couple of other peptidases. Do you remember? Where? No? 2 other peptidases. Can you see these guys? We saw them in the brush border. And we saw aminopeptidase. Now we see let's call it a sister, carboxypeptidase. So if this is a protein, every protein, as I mentioned before, has amino end and carboxy end. Aminopeptidase chops amino acids one by one from the amino end. Does that make sense? Carboxypeptidase chops them one by one from the carboxy end. That's it. Like imagine, I really like, we used the example of conga dance recently in micro class. I mean, you know, when people dance conga, did I name it right? They do like the long line, holding each other by the hips. The person behind holds the person in front, right? And you have like one person that's up front and one person that's in the back. Now imagine there's a monster, right? Or some guy with a gun. So one guy with a gun shoots people who are in the back only, like the last person, okay? That's aminopeptidase. There's another guy with a gun that shoots people, person that's up front. That's carboxypeptidase. They don't shoot people that are in the center. They only go from the sides. Does that make sense? That's your enzymes. Aminopeptidase and carboxypeptidase. Okay? It's not, I don't encourage any violence here. Just use it as an example. Okay? If you think that monster that eats those people is better, let it be monster. Okay? So now we have three enzymes, trypsin, chymotrypsin, and elastase, that chop the protein in large pieces, and we have carboxypeptidase that chops off amino acid one by one from the carboxy end. Does that make sense so far? So 4. Substrate for carboxypeptidase is still protein. Okay, just works slightly different. Does that make sense? Okay. Phospholipase. It breaks phospholipids. Okay. Where are we gonna find them? The phospholipids. The elements of what cellular structure? Phospholipids. Membrane. Okay. They also, you know, lecithin is phospholipid, so there's a bunch of phospholipids. Okay. Lipase. So phospholipids. What about lipase? What does it break down? Fat. So lipase separates glycerol and free fatty acids. Okay. Amylase. Carbs. There you go. But amylase doesn't, in this case, its function mostly is to take a gigantic molecule of starch and break it in smaller pieces, but not individual monosaccharides. Okay? So again, take this and break it in half. It's still big chunks, okay? But they're smaller than the original molecule. Cholesterol esterase. Cholesterol is usually bound with other molecules often. So it breaks down the covalent bonds between cholesterol and whatever it is bound to and releases cholesterol. And these guys, ribonuclease and deoxyribonuclease, they break down, well, that's going to be RNA, that's going to be DNA. Okay? They break them to the nucleotides. Does that make sense? Yes. Ribonuclease, deoxyribonuclease? Oh, they in all cells. Absolutely, they're everywhere. DNA and RNA are not, especially RNA is not stable molecule. Okay. Now, before we'll go on with the origins and stuff, let's take a look again at the substrate and the product. So, this 4, trypsin, chymotrypsin, elastase, and carboxypeptidase. What is the substrate? Proteins. What are the products? Smaller peptides, we usually call them peptides, but you can say proteins, and or amino acids. Phospholipase. The substrate is phospholipid. The products fatty acid, if it's phosphate residue, and glycerol. Okay? Lipase. The substrate is fat, not just fat, triglycerides. And the product, glycerol and fatty acids. Okay? When we'll get to the digestion, it's not a complete digestion. It's not all the way down to glycerol, but fatty acids, yes, absolutely. What's next? Amylase. Substrate is carbohydrates, large polysaccharides that are broken down to smaller polysaccharides, or we call them sometimes oligosaccharides. Okay? Cholesterol esterase, the substrate is bound cholesterol, the product is free cholesterol. It like unchains cholesterol from other molecules. Ribonuclease, deoxyribonucleases. Ribonucleases break down RNA, deoxyribonuclease, DNA, and the products are nucleotides. They chop to just pieces. They're super effective. Okay? We're going to review the origins and then take a break. Origins. Now, this is interesting. These guys are boring. They just released from pancreatic cells, from acinar cells. Now, trypsin. Trypsin is not released from acinar cells. Its precursor, so-called trypsinogen, is what's released. Does that make sense? Trypsinogen is released. When trypsinogen gets in the duodenum, it's activated by the enzyme called enterokinase. Do you remember what enterokinase is? It's not, no. Enterokinase sits in some other location. Yeah, but where? It's a brush border enzyme. Remember we talked about all the brush border enzymes? This guy, enterokinase. There you go, it activates trypsin. Okay? So its substrate is trypsinogen, it activates trypsin. And now look at this. When trypsin gets activated, it activates chymotrypsinogen, so you get chymotrypsin. It activates proelastase, so you get elastase. It activates procarboxypeptidase, so you get carboxypeptidase. It activates phospholipase, so you get prophospholipase, so you get phospholipase. Does that make sense? So enterokinase activates one pancreatic enzyme, and that activated enzyme, the trypsin, now can activate all other pancreatic enzymes. That makes sense? In my opinion, it's pretty stupid. Because the activity of the entire pancreatic juice depends on whether enterokinase is going to work or not. It's kind of a lousy. But it works, you know, we hear. Okay.
So then how are the last 5?
Are they just made? They're not activated, they're ready to go. Okay? They're like ready to eat. You don't have to cook them. Now, look at this list and try to recall the enzymes. Okay, we've got through this list. your short-term memory still keeps this. Let's go for a second. Oh, come on. Here. Which nutrients are broken down in the duodenum? Fat. You have lipase and phospholipase produced by the pancreas. Something else. Protein. And it's broken down to amino acids. Okay? If first protein is broken down by pancreatic enzymes like trypsin or elastase. Okay, so protein is broken down into large chunks, and then those two guys start to break it down into smaller chunks. That makes sense? So fat, yes. Proteins, yes. And sugars. So pancreatic amylase will break down into large chunks, like it'll break down maltose to dextrin, or sorry, it will break down starch to maltose or dextrin molecules, and then dextrose and maltase will break it to individual molecules of glucose. Does that make sense? Yes. Yeah, pancreatic. Well, when we say it takes effect in the duodenum, we have to understand that most of the time the lumen of the duodenum is empty, right? Because the amount of chyme that enters the duodenum and the amount of pancreatic juice that enters the duodenum, they are little amounts. So it all gets distributed over the walls of the duodenum. Does that make sense? So it's kind of a fairly thick layer of chyme and digestive juices on the walls of the duodenum. So in the kind of, so if this is the wall, red is the wall, okay? And now you have chyme, which is black, okay, mixed with the pancreatic juices, which are green, right? Here, you're going to have mostly pancreatic enzymes working. But as we get closer and closer to the brush border enzymes start to kind of play more and more important role. Does that make sense? That's your digestive enzymes. The next thing that we're going to chat about after the break, we're going to review the quiz, okay? Then we're going to chat a little bit, if we have time, about digestion and absorption. And I'm going to hand out the liver and duodenum quiz. Okay.